Welcome back. In this video, we're going to continue our discussion of the example from the last video by visualizing contour curves using Mathematica. Recall from the last video, we generated a vector value equation for 3 different contour curves on the surface of the function f of xy equal 9 minus x squared divided by 4 minus y squared. This is an elliptical paraboloid pointed downwards with a maximum value of 9. So it's a shift up on the z-axis, and then it's a flip. The thing, instead of pointing upwards like a cup, it points downwards like an upside down cup. We'll see that in a second as we graph it. When we looked at creating contour curves, we actually sampled 3 different planes. The first plane that we sampled was setting the output z equal to the constant 8. So we had a z naught equal 8. And we looked at the contour curve associated with this constant value z naught equal 8. And this contour curve was a set of ordered triplets x, comma, y, comma, 8, because the output was 8. We did some analysis to show, if we do mathematical analysis on this by setting the output equal to 8, we can show that this produces the ellipse x squared divided by 4 plus y squared equal to 1. Of course, we can use our work in lesson 5 to create a vector valued equation for this ellipse by recognizing that the x semi-axis has length 2, so this would be 2 times the cosine of t. This is the exact thing we did in the last video. This would be the sine of t, 1 times the sine of t, and then the height associated with this would be 8. I remind us because we're about to use both contour plot 3D to get the plane, plot 3D to get the surface, and parametric plot 3D to get the contour curve. We would do the same thing here when we looked at the constant plane z equal to 5 and intersected that with the surface. We got a contour curve that was defined by an ordered triplet where the x and y coordinates were given by this ellipse. Of course, we see in this ellipse that the x semi-axis has length 4. So if we defined this thing to be equal to 4 times the cosine of t, here we would have 2 times the sine of t, and then we would need a z component, which is just the height, which we said was 5. Finally, we had the viewer in the last video put this one together for yourself. You said that the contour plot associated with a height 0 was the intersection of the surface with the plane, the xy plane basically. And this was given by x semi-axis 6, and of course this would be times the cosine of t, y semi-axis 3 times the sine of t, and then we need a z height at 0. Let's go ahead and switch over to Mathematica, graph the surface, intersect the surface with the planes, and then graph the intersections, which we are going to call contour curves. Remember, these contour curves are in R3. I'm setting you up because in the next video, we're going to project them down and graph what happens in R2. Let's switch over to Mathematica. Bam! Here I'm in my lesson 7 examples notebook that we worked on previously. We're going to start with our function. I think we called our function f of x comma y. This is an explicit function. And we set it equal to 9 minus x squared. And of course we divide the entire thing by 4 because that was the equation. And we also subtracted y squared. This is an explicit function, which means we'll use the plot 3D command. We're going to use good coding mechanisms, so we'll never have to worry about making a stupid mistake in our code, and it's costing it 20 hours of your life. Okay, here we're going to graph f of x comma y, and we're going to let f of x, y range a bit. I think if I were to do like x from -6 to 6, and then y, if I go from -6 to 6, this actually took me a bit to think about. You can trust, well, no, don't never trust me as your teacher. You gotta always confirm things for yourself. But you could either spend 10 or 15 minutes by yourself, or you could listen to me say I did that before I actually started this video. So here you go, 0 to 9. Let's go ahead and take a look at this. Okay, so you got this kind of ellipsoid. You could actually drop this down to like -100 just to see what this thing looks like. Yeah, maybe that's too much. Let's try -50. Nah, too much still. Let's try -20. Yeah, there we go. You see that ellipsoid? Yeah. So let's go to 0 just to make this happen. There we go. Notice that the clipping style, Mathematica is basically complaining that that the domain that I've graphed actually doesn't actually produce output, so it had that gray thing. I don't want that gray thing there. And then you know my steez, right? You know my steez. My steez is, my style, I'm sorry, is that I like to do directive blue plots for some reason. And I also like to see see-through plots. So I'm going to go ahead and hit a 50% opacity in this one. And I'm going to need a comma there. Okay, and then you also know my steez because I don't like those damn plot. Get rid of those meshes. Who told you I want the meshes? Not a damn person. Why you always giving no meshes? Alright, there we go. So there's the mesh. Alright, we had just said that we would like to combine these with, maybe I need to zoom out here a little bit. Let's go ahead and see if I can do this. So I'm going to combine this plot. You know, let's do something kind of creative here, shall we? Let's call this surface F. Okay. Alright, and then we're going to go ahead and suppress this. So when I put the little semicolon there, it suppresses the output. So now I should get no output. Alright. Now we're going to go ahead and write show. And inside the show command, we're going to write surface F. Okay. So that gives me that. In addition to surface F, we just said that we wanted to intersect surface F with some planes. So the definition of the plane, we were going to use contour plot 3D. We've talked about this in a previous video. So I'm going to go ahead and define the plane. I think we said z equal to 8 was our first sucker, right? And we might as well use the same x, y, and z coordinates that I did up here. So here, this one would be z, of course. All right. And then we're going to do contour style. There we go. And I'm going to go ahead and write directive. Yeah, there's a little directive. Let's start with the color, I don't know. Do you want to do hot or cold first? I'm hot and I'm cold. I'm wet and I'm good. So yeah, let's do this one. Opacity, 50%. And of course, we're going to turn off the mesh. So we'll say mesh false. And we'll call these planes. So let's go ahead and do that. And now these are now variables that represent these graphics, and we'll go ahead and graph those together. Oh my god, isn't that just incredible? Don't you think you can do some crazy stuff with this? So that's the first plane, which was at height 8. Let's go ahead and combine these graphics together. So we're going to actually make a list of planes. The first one was z equal to 8. The second one I think I called z equal to 5 if I remember correctly. And the third one was z equal to 0. Because I have 3 planes, I'm going to need 3 separate directives. And I'm going to list my directives as a list. So I create open and close brackets. And you know my style. I like to do different colors. So maybe I'll go from hot to cold. So what is the next one? Yellow, I suppose, in color. And then the last one we'll do is green. So here it should be green. And now I'm going to have 3 different contour plots in the same planes graph. So this is a way to combine contour plots within contour plot. So if I were to actually unsuppress this output, you would see that I get something like this. Let's go ahead and suppress this output. What are you complaining about? Why are you complaining? Why are you getting mad at me? It's getting mad at me for some reason, and I forget why that is. Let's take a look. Oh, it's getting mad because my symbols are not correct. What are you talking about, Mathematica? Why you moaning? Why you moaning, huh? Let's see. Do I have the other one up here? I actually finished. Oh, of course. I need a comma right there. Okay, that's pretty fun, isn't it? So the red one is at the z equals 8 because the first one's red. The yellow one's at the z equals 5, and the green one's there. And then we just said that we could plot the contours on this surface using parametric plot. So let's call these contour curves. That's going to be the name of this graph. And it's going to be the output of a parametric plot 3D command. Okay, so we'll go ahead and suppress that. Remember, in parametric plot, generally I'm going to do one at a time. So here we said that the first one I think was going to be, what was this? 2 cosine of t. The next one was just going to be sine of t. And the last value I think was 8. And then in general, when we were doing these curves, we said that t went from 0 to, I think, 2 pi, right, if we wanted the entire circle, or in this case, ellipse. And then, of course, we would want to do plot style. And plot style would be, yeah, maybe we just go ahead and circle those because I'm going to expand this. Directive. And what do we got? I think the first one we were going to do was red. And let's go ahead and increase the thickness of this from the standard Mathematica thickness. And we'll go to 0.008. That seems to be pretty good. Oh, of course, I need to actually say, hey, Mathematica, please combine this using show. So this is kind of cool. There's my curve. Let's go ahead and increase the thickness just a bit. Okay, there's my contour curve. That red curve at the top, that's the contour curve. And notice it's in R3. Oh man, I don't know if I like that red on the bottom because it turns into orange when it's mixed with yellow. It's almost like we're in art class, right? Okay, so this gives me the first contour plot, and I can now combine this with other contour plots by making a list of parametric plots. So here we go. We'll go ahead and push a comma right there. The next parametric plot we were going to do, I think we said had a x semi-axis length 4, a y semi-axis length 2, and the height of that one was at 5. Look back on your notes to make sure I'm not saying anything crazy. So here we said that the first one had this directive, these attributes. The second one we were going to call, what did we call it again? I think we called it yellow, didn't we? I'm just crazy about yellow. Okay. So there's my second contour plot. See it? There's red, there's yellow. And then the third one came from intersecting with the height 0. And I believe we said, ooh, sugar. I believe we said that the height of that one was at 0. The x semi-axis was 6. The y semi-axis was 3. And we wanted that one to be green. So let's go ahead and create that green one. Boom. Okay. Now, what I wanted to show you was we think about contour plots as coming from the intersection of the plane with the surface, but in reality, we don't need the planes. The planes are just kind of a way that we think about this. Those are the contour plots. Those three things on the actual surface. That's the contour plot. And what's really cool about that is, imagine that you were skiing or walking on a mountain and you walked along those curves. Do you see that all the output values along those curves are constant? Pretty exciting, right? Contour curves are in R3. Up here in this coding, what I did is I actually set the output of my graphic equal to a variable name. So here my first graphic I called surface F. So now that's going to be the plot, the output, the graphic object that I created. The second graphic, which was a combination of all three planes, I called planes. And then the third graphics object, which was a combination of all three parametric plots, I called contour curves. And then what I did is, instead of having to combine everything within the show command, I could modularize separately. I could do each code separately, and then graph them by just typing in the titles, right? In the next video, we're going to see how to transform contour plots into level curves. And that's, level curves are in the domain, contour plots are in R3. Let's switch over to the next video. See you there.